After we know how to draw the Bode plot, so now we are going to learn how to use this Bode plot in order to investigate system stability or examine the system stability. That means if we already draw the Bode plot and we can check if this Bode plot is if the system of this Bode plot is stable or not. So like we did previously with the root locus and with the rough table to investigate the system stability. So the gain has a direct effect on the stability of our system. The gain means the value of k for transfer function has a direct impact or direct effect on the stability of the system, because the open loop gain here, the change in the value of the gain k will cause the movement of the closed loop transfer function poles, uh, and the poles will be moved from the left side to the right side, so the system stability will be effective. So in order to use the Bode plot here to investigate or examine the system stability, we need to know two main factors or two main parameters. The first we call it here gain margin or GM here, gain margin, and phase margin, which is FM. So these two parameters are very important to know the system stability based on or by using Bode plot. So the gain margin definition here is the change in the open loop gain, the change in the open loop gain expressed in decibel here. We are talking about the value of dB here. When we talk about the magnitude, actually, we are focused on the magnitude uh, or the log magnitude bar of the graph. We said the Bode plot has two plots. One is log magnitude, the other one is the phase angle. Okay, so for the log magnitude here, so the gain margin is involved with the log magnitude and the phase margin is involved with the phase angle plot. So this is the express in dB required at 180. That means what is the value of the gain in dB at the 180 phase shift in order to make our system unstable. So this we call it gain margin. So the gain margin is a value at which at this value our system will change from stability case into instability case. It's equivalent to the value of the crossing of root locus. If you remember when we said root locus crossing the imaginary axis, and this point of crossing imaginary axis is important because it decides if the system is still stable on the left side or move to the right side, so become unstable. So this is the gain margin. The phase margin definition here is the change in the open loop phase shift required at unity gain. Unity gain means at the crossing. When we say unity gain, we are talking about the crossing point of zero. Okay, unity gain means log or 20 log 1 equal to 0. We are talking about the or the x-axis of the or the axis of the frequency here to make the closed loop system unstable. Also, it is a marginal point or values uh, in the based on the phase plot, and it used to identify system stability. As we can see here more clear from this is actually this is the equation. We are going to see the gain margin and phase margin representation in the Bode plot graph, but before that we need to know that the gain margin value here is equal to, this is the equation to find the gain margin, equal to negative 20 log gain margin of j omega when omega equal to gm. The value of omega here equal to omega gain margin. So we are going to see how to find this frequency omega gain margin, and so it's equal to negative lm omega gain margin value. The phase margin here equal to 180 plus gauge omega when omega equal to omega phase margin. So our task will be identify the value of frequency for the gain margin and phase margin calculation. When we know this frequency, we are going to identify if our system is stable or our system unstable. In order to make our system stable, both gain margin value and phase margin value must be positive values. So if you say gain margin equal to 10 dB, that means 10 dB is positive. So our and phase margin, for example, equal to 150 degree, so positive. So both positive. So our system is stable. If one of these values, gain margin or phase margin, is negative, that means, for example, we have negative 3 dB, negative 1 dB, whatever is the value, but it is negative for the gain margin, or negative 45 degree, negative 30 degree. So one of them is negative value. So in this case, we are going to say our system is unstable. For marginal stable here, marginal stable is equivalent to the value of the gain when the crossing here, if you remember in the root locus. In the case of Bode plot here, for the Bode plot, the system will be marginally stable if both gain margins and phase margin are equal to 0. So if you calculate the gain margin equal to 0, the GM equal to 0, VM equal to 0, so in this case you are going to say the system is marginally stable. Okay, so according to this graph, so if you have this graph represent the Bode plot of your system, we already draw it, we found it, the Bode plot. We have some graph here, we don't know, I mean, the code to complete this graph, but our focus will be on the crossing of the log magnitude graph with the 0 axis, this point, and the crossing of the phase graph with the 180 degree axis. Okay, so this is 2 points are very important, because this point will give you the point of frequency for gain margin, and this point will give you the point of frequency for phase margin. Okay, so this we call it omega Vm. As we know that the log magnitude graph and the phase graph here, both are drawing with respect to the frequency. Okay, since that means the value on the top here, if this one is 1 hertz, for example, this will be 1 hertz. If this one is 10, this will be 10. So it is the same. If we have these two graphs, actually we can just draw straight line from the crossing of the log magnitude into the phase margin frequency here. So when we draw here, the value which is here, this margin, actually we call it the phase margin. We draw line from the crossing point with the 0 axis or the 0 dB axis, then the value between the phase plot and the 180 represent our phase margin. Okay, then from the crossing of the phase plot with the 180, we draw another line to the top, and here this area or this interval represent the gain margin value, which is the difference between the 0 dB and the plot of our gain or magnitude or log magnitude value. Okay, so this is the log magnitude, and this will be, with this we call it actually gain crossover frequency. Crossover frequency, that means at this point the gain will change from positive values to negative value of the dB. The same here, at this point here we call it phase, that one related to the gain, because we are talking about the log magnitude, and here is related to the phase. For this one we call it phase cross frequency. Okay, so these two cross point are very important, because from this point we are going to find the gain margin, the phase margin, and from this point of crossing we are going to find the gain margin. After we find this value, we are going to apply our formula. We said gain margin equal to negative the value of this GM. Okay, according to this formula here, gain margin will equal to negative of the value of log magnitude of cross or magnitude or phase cross frequency. Okay, so for example, if this value GM here equal to until, I mean, from 0 to, for example, negative 10 dB, that means our gain margin will be negative 10 dB, so it will be positive 10 dB. If it is positive, that means our system will be stable if the phase also is positive. So both values here should be positive, gain margin and phase margin. We are going to see an example here. in order to identify or examine the system stability according to the body plot that we have from MATLAB here. So this is body plot is drawing for one existing system, and the top part is for magnitude, and the down part, the bottom part is for the phase. So the blue line here represent the magnitude or the log magnitude plot, and the blue here is the phase magnitude plot. As we said, we need to identify from this graph, the first we need to identify the cross frequencies. So the cross point frequencies for the magnitude and also for the phase. So this is the first, which is the gain crossover frequency, and here we have the phase crossover frequency. The gain crossover frequency represent the intersection between the plot of the log magnitude with the 0 dB line. This is 0 dB line. So the crosshair, we call it the gain crossover frequency. Okay. The second one, which is the crossing between the phase plot with the 180 line, here with 0 dB, here with 180 phase degree, and this will be give you the crossover or phase crossover frequency, which is this point. Okay, after we identify the point, we draw a line from this point until we reach to the plot here for the phase. So the difference between this point on the plot, on the phase plot, and the 180 represent our phase margin value. So if we, when we use MATLAB, we just indicate or put the cross the indicator is here, so it shows us the value of the phase. The value of the phase at this point is equal to negative 117. So this is negative 117. If we put it here in our equation for phase margin, which is 180 plus the angle, as you can see here, this is the formula, 180 plus the angle at the crossover frequency. So it's 180 minus 117, so it will give you the value of the gain margin, which is positive 63 angle. This is for the phase margin. For the gain margin, also the same. We are going to draw a line from the crossover frequency point here for the phase to the top, to the plot of the gain, and we find what is the value of, or what's the difference between the 0 point and this point. So this is the 0 point, and here the point is negative 29.5 dB. We use the formula which said gain margin equal to negative of the log magnitude. This is the formula here, negative of the log magnitude of our system. Okay, so the gain margin equal to negative log magnitude. That means whatever is the value here, we are going to multiply by a negative sign. So in this case, it is negative 29. You multiply by a negative from the formula, so negative of negative will be positive 29. Since you have positive gain margin, positive phase margin, so your system is stable. Because the gain margin is positive, the phase margin is positive, so your system will be stable. So the system at this frequency, at this gain, will be stable here. Okay, in order to understand what will, how it looks, how it will be looks if the system is unstable, or how the body plot will looks if the system is unstable, we can see the example number 4 here. So in example number 4, we have the body plot or the log magnitude plot, and the log or the phase plot here, the two plots, and on the same frequency actually here, from 0 from 0.1 until, for example, 10 to the power of 5. So what we are going to do, we need to identify where is the crossover frequency for the gain crossover frequency, and the phase crossover frequency. We said the crossover frequency is for the phase with 180, for the gain is with 0. Always you the cross, that means cross with the 0 dB and with 180 degree. Okay, after you find these frequencies, actually you are going to draw line from the top of the plot of the gain until you cross with the gain, I mean with the plot of the phase. Okay, so the difference here will represent your phase margin. I mean the phase margin value here will be the difference. We said it is the difference. If we want to calculate, we just need to find 180 plus the angle. So the angle at this point is represent negative 53. So 180 plus minus negative 53, it will give you a negative phase margin. Since you have negative phase margin, your system will be unstable. Whatever is the value of the gain margin, is it positive, negative? It doesn't matter, because if one of the gain margin or phase margin is negative, so your system will be unstable. Okay. But in order to find also the gain margin, just to know the value, so the gain margin also here, this is the crossover frequency or the phase crossover frequency. We draw line to cross with the magnitude. From the magnitude here, we find the value of the log magnitude here. So the magnitude equal to negative 20. We said the formula said negative of the magnitude, so it will be negative of negative 20, so it is positive. So the gain margin is positive, but the phase margin is negative, so your system is unstable. So this is how to use the Bode plot in order to find or examine or test the system stability. So if one of the gain margin or phase margin is negative, so your system is unstable. Another example here is example number 5, also on the same, to identify the impact of the value of the K or the gain K here on the system stability. For example, in the first case, we have the gain K equal to 10. In the second case, we are going to have the value of the K equal to 100. Then we are going to compare what is when the system will be stable, or what is the impact of the gain on the system stability. Okay. So for this case, actually, we are going to draw this Bode plot of the system by using MATLAB also. So it will give you this figure, for example, here. In the first case, in the K equal to 10, if the K equal to 10, we said the value of the gain K will give you 20 log K. So if you have 20 log 10, so it will be 20. So you have 20 value of the gain here. So the overall graph by using MATLAB, it will give you this log magnitude graph for the magnitude, and this one is for the phase. Okay. So in this case, if we want to know if the system is stable or not, we want to find the crossover frequency here. So this is at this point, we are going to draw until this point, then we find the difference between the 180 and the crossover frequency. So the angle here is 21 plus 21. The phase or the phase margin is plus 21, and the gain margin in this case will be positive 8, because it's actually it is negative 8 here, but it will be negative of negative 8, so it will give you positive 8 dB. This is in the case of the K equal to 10. So the gain margin is positive, the phase margin is positive, so your system is stable. If we increase the value of the gain to 100, that means the component of our transfer function here, transfer function, how many components we have? We have 4 components. One is the gain, one is integral pool, and 2 are first order pools. Okay. So if we draw this one alone, this one alone, alone, then we combine on, so we are going to obtain this Bode plot. Okay. So in the case of the K equal to 100, that means the value of the gain plot, which is 20 log 100, will be different. It will be 40 dB. Instead of starting at 20 here, we start at the 40 at this point. That means we are going to shift our log magnitude plot. See, this here start at 20 because we have 20 log 10. This gives you 20. So we start at the 20 dB here. But if we have K equal to 100, so we start at 20 log 100, which is 40 dB. So now it's like we shift up our log magnitude plot. When we shift it up, this part will go up here. So the crossover frequency will be changed. Okay. If the crossover frequency is changed, so the value here, this is the crossover frequency for the for the phase with 180. If we draw here, we found this is our gain margin here. This is the difference. It's become on top of the 0 dB line. This is the 0 dB line, and our magnitude here or our graph become on on the top of it. Okay, but here it is on the bottom of the 0 dB line. This is the 0 dB line, so the line become on the bottom here. So if we calculate the value here, value is the value is 12 dB, but based on the formula it will be negative of the log magnitude, so it will be negative 12 dB. So in this case the gain margin is negative. If the gain margin is negative, that means there is one of the margins is negative, so the system will be unstable whatever is the value of the phase margin. Okay, but also if we want to calculate the phase margin, also the same, we are going to find the crossing frequency for the magnitude here, or the the gain cross frequency. We draw the line until the plot here for the phase, and then we find that is the difference between the phase and between the 180 line. Okay, so this difference we are going to find the value of the gain margin, which is also negative 30. So both gain margin and phase margin are negative, so our system will be unstable. Okay, so this is how to use the gain margin and phase margin in order to investigate the system stability. There are more exercise and examples in the slide. You can refer to it. Thank you.